Well, thank you so much, Masashi, for the kind invitations and the introduction. Yes, so I will try to keep it within 1 hour, but yeah, if there are many questions and interests,
Yeah,
I can
up
give
to
more
you, up to
detail.
you.
Um, yes, so well, I'll try to give a talk which is more like an overview talk based on, well, three main papers. One of which is actually quite old, plus many other things. So there are some references at the end. Because I wasn't sure what the background of the audience, so hopefully it will make sense. But it's very much concentrated on integrable aspects, integrable systems, with a view to formulate integrability um, in the Lagrangian setting as opposed to a Hamiltonian setting. So the plan, because I will talk about integrability a lot, and integrable systems a lot, I will review and introduce some notions of integrability that are going to be useful for my purposes. So the main two notions will be integrability in the sense of Liouville, so Hamiltonian integrability, and lax integrability. Then I will say, well, I will introduce a new criterion for integrability, which is purely variational and is known as Lagrangian multiform theory. I will explain why it's a good criterion for integrability that we can sort of accept as the same standard, same level of standard as in the two previous notions of integrability. And then the rest of the talk will be to address the question of constructing examples of Lagrangian multiforms. So once you have a theory or a criterion for integrability, of course, the major work is to actually construct examples in an efficient way that satisfy the conditions of the criterion. So the examples or the method for construction, first I will review some key ideas on the simplest example, the one that was done historically. And then I will explain what led to the more advanced and more general construction um, by extending this simple example in quite a few directions. And by doing so, we will see that the classical Yang-Baxter equation, which I will introduce, plays a crucial role in this generalization. So in this talk, everything is classical. So it will all be classical field theories. There will not be anything quantum. So I will take an example to illustrate various notions of integrability. So the two main ones, Hamiltonian or Liouville integrability and lax integrability, on a model called the nonlinear Schrödinger model or equation. So it might not be the model you're most familiar with, but in many ways, it's one of the simplest in terms of the underlying Poisson structure and algebraic structures. So that's why it's very useful to understand it first. And it's one of the three main integrable field theories that people use to illustrate ideas. So you usually have KdV, Korteweg-de Vries, nonlinear Schrödinger, or Sine-Gordon. That's kind of the three prototypes. So what's the model? Consider two complex scalar fields, and these are the equations of motion. So the nonlinearity is here in this cubic term. And the linear part is of Schrödinger form, so that's why it's called nonlinear Schrödinger. And in fact, historically, the famous model, physical model, is obtained by imposing some reduction. So that's the model. G is some coupling constant, and you can think of it as a non-relativistic phi to the fourth theory, if you know that, if that's more appealing to you. Okay, so that's the model, but What is particular, what is special about this model, it is that it is integrable, and we're going to see why in a minute. So first of all, it's an example of a Hamiltonian field theory. So you can formulate these two equations in a Hamiltonian form. This is the Hamiltonian density, and this is the Poisson bracket that you use between the two fields. So this Poisson bracket will be useful because it's going to come again later in a different form and will be the origin of the classical R matrix. Okay, so this is a Hamiltonian formulation of the model. Oops. But it also has, and that's what makes it special in a way, it also has a lax pair formulation. So this system is equivalent to a zero curvature, or maybe you know this condition more as a flatness condition of a lax connection, um, which involves a lax pair. And if you choose the lax pair the right way, you can see that imposing this condition is equivalent to having these two equations holding. So let me show you what U is explicitly. So first of all, both U and V in that case are 2 by 2 traceless matrices. They depend on the spectral parameter, which I call lambda here. And they have quite a typical structure, and that structure will become very important in the future. So the first one, U, is of this form. So it's a first degree 1 polynomial in lambda, and each matrix, so Q0 is just minus I sigma 3, where sigma 3 is the usual Pauli matrix, and Q1 is this off-diagonal matrix. So both of them are traceless, which means that we're working with the SL2 Lie algebra. And the explicit form of V is not so important for us, but what's important is that it's a polynomial of degree 2 in lambda. And similarly, so these are the same two matrices, Q0, Q1, and then you have an additional one, which can be determined to make the zero curvature work. So that's the story so far. So why is it special, the model, and why does the existence of a lax pair allow you to see that it is special? So there is a fundamental connection, or sorry, let me move. There's something in the way of my. How do I move that? I can't see my own sentences. There we go. So, so far I presented two facets or two aspects of the same model. It's a Hamiltonian field theory and it has a lax pair formulation. Actually, there is a very, very deep connection between the two pictures. And the most direct way to see this connection was found by Sklianin in the 70s, late 70s, early 80s. And it's actually to take the Poisson bracket on that I used on the fields and to insert it directly and see how it can be reformulated in terms of the lax matrix U. So if you know the Poisson bracket of Q and R, you can try and see what the Poisson bracket of U should be. So the meaning of this expression on the left is that you take U for some position X and Y and some different parameters, spectral parameters, lambda and mu. The indices Y and 2 mean that it's a tensor index tensor indices. So what I do is you place U1 means the matrix U is in the first tensor factor of a tensor product, and it's the identity in the second one. So what this does for you is that you put together all the possible Poisson brackets between all the entries of U. So this is a 4 by 4 matrix of Poisson brackets. And the beauty of Sklearning insights is that this can be reformulated as a commutator of a specific form. And there is an object that appears in this commutator that is of central importance, and it's the classical R matrix. So this is known as an example of an ultralocal Poisson algebra. So Poisson algebra because gives you the structure of the Poisson brackets and some algebra of fields. And ultralocal is because you have this Dirac delta appearing. It would become non-ultralocal if you had additional terms involving, for instance, the first derivative of delta. In turn, this is what will give the name to all the theories I'm looking. So the reason why I will talk about ultralocal field theories is because they're all based on Poisson algebra of this type. So what is this special object? So in that case, when you do the calculation explicitly, you can recognize that it takes a specific form. So it's a 4 by 4 matrix of this form. So actually this object is not random, it's a permutation operator, but in matrix form it takes this explicit form, quite simple. And it has this special rational dependence on the spectral parameters. So that's why it's called the rational R matrix. And it enjoys this property, which means that it's called skew symmetric. So when you swap lambda mu, space 1 and 2, you pick up a minus sign. If you're worried about, well, you should be worried about the Jacobi identity for this Poisson structure, and it turns out that it is ensured if R is a solution of the classical Yang-Baxter equation, which takes this form in general. It's a condition on R, and well, this explicit form is one of the simplest solutions of this equation. So that's the first deep connection, is that you can encode the Poisson structure of the Hamiltonian description directly into the Lax matrix. And as a result of that, what is very nice is that the zero curvature equation itself then becomes Hamiltonian. So if you compute the time derivative of u using the Hamiltonian I showed you before and do some calculations, you can recognize that it takes the form that will give you the zero curvature or the flatness condition. So that completes the sort of the connection between the two pictures. And this connection is done via the R matrix. So there is an even bigger and more important consequence, which now really explains why we're talking about integrable systems. So when you have a Lax pair, the importance of it is that you can construct lots of higher conserved charges, which happen to be Poisson commuting with respect to the Poisson structure that you can introduce, that I have introduced before. And now there comes an important idea. So more than just seeing them as conserved charges that commute with the Hamiltonian and among themselves, what you can do is to interpret them or use them as Hamiltonian themselves, and then use them to define their own differential equations or their own flow. So in equations, what this means is the following. So now imagine that I take one of these higher conserved charges, higher Hamiltonians, and I want to calculate, like before, the Poisson bracket of this Hamiltonian with u, and I define this as the time flow on u for some other time. Okay, so the word time here is not the physical time, it's just some variable to define your flow. Then you can show that it will also take a zero curvature form, where now a matrix, a new Lax matrix appears, which I've labeled with this little k, superscript k, to remember it corresponds to a different Hamiltonian at a different time. And what happens is that each of these higher Lax matrices is also of polynomial type and of degree k. So there's really a pattern appearing in this hierarchy. And what I explained in the first few slides, if I go back, is just the beginning. So here you have, you see the first time t1, and then you have the second time t2, and then you keep going, and you build a hierarchy of equations which are all compatible with each other. And the compatibility is this last line here. So from the Hamiltonian point of view, it is possible to impose all these equations simultaneously on the same objects because the Hamiltonians Poisson commute. That's the property of these conserved charges. And if you translate or look at what the manifestation of this in the Lax pair or Lax matrix sign, it means that you have now not just one zero curvature equation, but an infinite collection of zero curvature equations that involve all the possible pairs of Lax matrices and times in your hierarchy. So the collection of all these equations, it can be taken as defining the integrable hierarchy that contains the NLS as the first model in the hierarchy. Does it make sense so far? Okay. Stop me at any point if it's not clear. So now we've put together Hamiltonian description and Lax description, and we've introduced the notion of a hierarchy. So that's a really, really important feature of integrable systems. They don't live on their own. It's not just one model is integrable. It's really, really more profitable to think of them as part of a hierarchy of commuting flows. So that's what I've summarized here. We get an infinite collection of zero curvature equations for all the Lux matrices. And the thing is that they're all Hamiltonian. So now you can really extend this equation that was really related only one of the VKs with a U to all possible pairs of V's. And what this buys for you is that then the original Lax matrix, so the one that starts the hierarchy U, you can just view it as one of the Lax matrices. So I may as well relabel it. It's just one of all the Lax matrices, nothing special about it. And similarly, an important conceptual idea is that then what I called X so far, when I was worried about the physical interpretation of the model, from the point of view of a hierarchy, is just one of the times of the hierarchy, so one of the independent coordinates. So I can put everything on the same level now. All the times and all the Lax matrices in the hierarchy are on the same footing. So just because if you've never seen that before or not so used to this idea, let me show you what this construction gives you if you go um, to the next level. So if I now look at the time t3, that would correspond to the conserved charge or the Hamiltonian after the Hamiltonian for nonlinear Schrödinger, you get a certain equation. Okay, it is what it is. So two equations for I and t. It's now third order in the x derivative, which now if we call t1. It's got some specific nonlinearity and is known in the literature as the modified Kurt-Avogadro's equation. So, okay, it is what it is. And these two equations are part of what's known as the Ablowitz-Kopp-Newell-Seger hierarchy. So this will be my motivating example for everything before I explain the generalization. And according to the general scheme, you can check it can be written in this way with the Hamiltonian, and it's got a zero curvature. Oh, sorry, there's a typo here. And the corresponding Lax pair is of degree 3 in lambda. So there is really a pattern here. So this last line really shows a pattern. So all the Lax matrices are polynomials of a certain degree with coefficients in a given Lie algebra, which is SL2C in that case. And we will exploit this later. Right, so this was really a short course on various notions of integrability. This is the story that has been developed over the last 50 years. Lax integrability. Hamiltonian integrability is even older. It goes back all the way to Liouville. But as we know in fundamental classical mechanics and theoretical physics, uh, there's a Lagrangian counterpart to a Hamiltonian description. So it turns out that actually the Lagrangian formalism was a bit left out of the integrability developments. The focus was mainly on Hamiltonian formalism and together with Lax formalism, as I've just explained, and how they get together. So what about describing integrability with Lagrangians? So to go back to the example, it's not, you can convince yourself that both the nonlinear Schrödinger and the next one in the hierarchy, the modified KdV, they're both variational. And it's not too difficult to compute to find their Lagrangian densities. So you've got some kinetic part here, potential, and then, okay, the next one is a bit more complicated. But there is an explicit expression, and if you take the action for the first one, do your usual variational principle, the earlier Lagrange equations will give you the correct equations. But these two Lagrangians on their own, they don't tell you anything about the special property of being integrable. And in fact, yeah, you wouldn't know that they are special just by looking at them. So how can we capture integrability and also the key insight, the fact that they belong to the same hierarchy in a Lagrangian setting? That's kind of the key question. So I will discuss two aspects from now on. So the first aspect is the answer to the question how to define a variational integrability criterion. And this is where the idea of Lagrangian multiforms appears, which was originally proposed in 2009, actually in a very different context, in a context of discrete integrable systems. But I will present the idea in the context of two-dimensional field theories today. And once you've built uh, a theory that you're satisfied, gives you a variational integrability criterion, the second aspect is, okay, how to construct effectively such objects, such Lagrangian multiforms. So these are the two questions that I would like to discuss now. So the first question, or the first aspect, as I said, so you can do it for finite dimensional integrable systems, 2D, or 1 plus 1D field theories, which I will explain today. You can do 2 plus 1 field theories, for instance, KP. So the ideas are always the same. You just adapt the formalism. The key ideas are the following. So first, we're going to appropriately generalize the traditional action. And accordingly or consequently, we're going to have to introduce a generalized variational principle that captures integrability. So how do you generalize the traditional action? So if you have a two-dimensional field theory, say in 1 plus 1 space-time, x and t, you consider an action with a Lagrangian density. U here is just a letter that denotes generic fields. It could be scalar fields, vector fields, whatever you like. And the square bracket notation means that obviously depends on the field, but usually first derivatives, sometimes higher derivatives, higher jets. So whatever you need to describe your favorite theory. And you have essentially a volume form which you integrate, say, in R2 if you work in this spacetime or whatever spacetime you need. So the first step is, okay, is to take on board the idea of a hierarchy. So, well, if I want to describe something integrable and a collection of equations that belong in an integrable hierarchy, I need to consider not just two of the coordinates in the hierarchy, but all possible coordinates. So I replace this volume form in 2 dimensions by a collection of two forms labeled by the times of the hierarchy. And to each pair of times, I associate a Lagrangian coefficient or some coefficient, which in general has a similar structure as the one you would usually use, with one distinction. So now in here, you will have the fields, U, but also its partial derivatives with respect to all possible times in principle, and maybe higher order. So, in summary, I substitute this volume form to a two form, and I define an action now with one new key ingredient. It's not going to just depend on the field configurations, but it's now going to depend on this sigma, which is a surface, so a two-dimensional surface, because I integrate a two form, over the multi-time space, so which is the space in which all the times of the hierarchy live. So we have now two ingredients. So a traditional content, the field content, but now a surface over which I integrate these two form. And you'll see that this new ingredient is what will encode integrability if I use it properly. So that's the second step. Now I need to introduce a generalized variational principle. So what does it consist of? The first consists of two steps. So the first one is you impose a variational principle, the usual least action principle with respect to the field configurations, but now you require that it should hold for arbitrary surfaces, sigma in multitime. Sorry, there's a typo here. And this idea, or the idea behind imposing this principle, is the following: is to impose the compatibility of the flows between themselves. Because if you have a surface in multitime and you require a minimization for all possible embeddings of the surface, or every possible surface is, sorry, embedded in the multitime, you sort of explore the compatibility of all the time directions. So that's the intuition sort of behind this principle. And there is a second step which really takes you all the way to integrability. So now on solutions of the equations that you obtain from the first step, you are requiring a stationarity of the action with respect to the surface now. So that should not hold identically. So that's the meaning of this weaker equality. That should hold when U is on solutions. And now, if you like, it's like a least action principle, but with respect to the surface, defining your action. So that's the new ingredient. So what are the consequences of this generalized variational principle? So the consequences of the first step is that you obtain not just your usual Lagrange equations, but more equations, because of the requirement that they should hold for any surface sigma. So you do recover the usual Lagrange equations, but for each Lagrangian. So here I'm only showing the form of the equations in the simplest case, where your Lagrangian is first jet or first order in the velocities. But now you have more constraints, more equations, which actually constrain what the possible Lagrangians should be. So, it's not every theory that is going to work, and you would expect that, because it's not every theory that is integrable. So these equations, they take this form. So one tells you that on solutions, the Lagrangian corresponding to time I and time j should not depend on the velocity corresponding to another time. And however, when they coincide, so when you take the partial derivative of Lij with respect to utj, so that would define some canonically conjugate momentum in general, well, that should correspond to the same quantity you would compute using a different time k, the different velocity, with a different Lagrangian, but the same I. So, okay. We sometimes call it the common momentum equation. So to put together, the second one, the idea is that in principle they could select some allowed Lagrangians, And then you look at the type of equations that you get, which are the traditional Lagrange equations for each I and j. There's a second step, which is even more stringent. So once you've got these equations, you could try and say, okay, on solution of these equations, you require the same, the second principle. And it tells you that via Stokes' theorem that actually your two form should be closed on solutions. So this will become later important very soon. In components, you have this expression of the fact that the two form is closed. And remember that this is required only when you are on shell or on solutions. So why is this a good variational criterion for integrability? Why, you can postulate those things, but maybe it's useless. Well, it's not useless. First of all, it's not useless because we managed to fit a lot of known examples into this framework. But the single most important argument is that you can show that the closure relation is equivalent to the usually accepted criterion for integrability in the Hamiltonian framework. I won't say much more than that. So this takes a bit of work. For finite dimensional systems, it's very easy. Well, very easy. It's proved rigorously. For field theories, you have to work a little bit more. And some aspects are still under consideration, but this is the key idea. So you can forget about Hamiltonian picture if you're convinced that it's a good criterion, and then just accept that what I've just presented, so the set of the generalized variational principle is a good criterion for integrability. Are there any questions at this stage? Okay, right. So the second aspect, now I've defined what I think is a good framework. We need an effective construction for such objects, for multiforms. So I'm going to use everything we've learned from the example of AKNS. So in short, how to construct all the Lagrangian coefficients, Lij. So essentially, the summary of what we've been doing over the last few years is on this simple diagram, especially the right-hand side. So a good guiding principle was to first know what type of integrable hierarchies do I want to reproduce variationally. And I want to reproduce all the possible integrable hierarchies that can be described as zero curvature equations. In particular, the one I described as an introduction. And I know that this side of the story via the R matrix is related to the Hamiltonian aspects of things. So you can put everything together to have a consistent theory. So, but the guiding principle is, okay, let's find all those Lagrangian coefficients such that I have a multiform which produces this hierarchy of Lax equations and zero curvature equations as its variational equations. So that's the goal. So there are several sources of inspiration, which I'm going to explain in turn. So think the Flash-Canuel-Ratu algebraic construction of the hierarchy I presented. So I will tell you more about that in a minute because this was quite important. Then there is an idea of generating formalism, which was advocated quite a lot by Frank Nijhoff, but is also already kind of present in the first Flash-Canuel-Ratu. And to really come up with a good form for the Lagrangians, the paper by Zakharov Mikhailov in the 80s was very inspiring because it essentially gives you an important idea as to how do you find the Lagrangians for zero curvature equations. Okay, so the key observation of Flash-Canuel-Ratu is that let me go back to the collection of all the zero curvature equations. So we convince ourselves that an integrable hierarchy is well described by an infinite collection of zero curvature equations for lax matrices that are polynomial in that case. And their observation is that you can repackage all these equations, which are, we can see, sort of partial differential equations, into a collection of ordinary differential equations, so infinite number of ordinary differential equations for a single object, Q here, and Q is a series, is an infinite series in 1 over lambda here. And remember, these little QJs, they live in SL2 and they contain the fields, QR and their derivatives. And the lax matrices are polynomial. So that's the observation, and they cast this observation in an algebraic setting. So in fact, you can interpret all this in the loop algebra, SL2, tensor product with Laurent series in 1 over lambda. So this is the loop algebra, this type of objects that I'm interested in. And an important aspect to carry out the description as a dynamical systems or as an infinite set of ODEs is a decomposition of this loop algebra into positive powers. So the LJ plus are just a collection of polynomials. So that's the significance of this P plus here is a projection of a general element on its polynomial part. And then the rest is just the object of this form, so that have an infinite tail in negative powers of lambda. So Q would live in LG minus. Okay, so the idea is that you can reformulate an entire collection of zero curvature as an infinite collection of lax equations of this form for a single object, and you can cast everything in the setting of a loop algebra. That's one important observation. The second observation is that the idea of compounding hierarchy, so is to assemble an infinite number of differential equations into a generating equation which contains them all as formal series. So it's like a trick, really. But it works really well. So let me assemble all the time derivatives into this generating series in 1 over mu for some other spectral parameter mu. Let me use the expansion that everyone knows of this rational fraction, but in 1 over mu. So this iota mu means I'm expanding in 1 over mu, because I could also be expanding in lambda, but that's not what I'm using here. So it takes this form. And then you make a simple observation. So if I take a polynomial of a degree k and apply to it or multiply by this generating function with 1 over mu, you rearrange your series, and then you realize that it takes this form, where q mu is just this infinite series in 1 over mu now. So what it means is that you can repackage this infinite collection of lax equations for Q into a single generating equation of this form, which is also of lax form. So we've got theta. But it only involves the object Q now and this rational fraction, which will become important because it's not just random. It is a special one. So if I summarize the two steps I've just done, I take the infinite collection of zero curvature equations that describe the hierarchy. I repackage it as an infinite collection of lax equations for this series. And this collection, I repackage as a single generating lax equation. So all the information I want about my integrable hierarchy is contained here as a set of equations. So that's the equation I'm going to try and reproduce variationally. So the last step is to use Zakharov-Mikhailov trick to know what form of Lagrangian would work. And there is this idea that you parameterize this series Q, which is an object in a Lie algebra, a loop algebra, but you parameterize it as the adjoint action of a group element, which is itself a series, on a constant element, Q0, here for this example. So it looks like a simple trick, but doing that has actually a deep algebraic interpretation in terms of coadjoint orbits and the theory related to that. If you know about it, it's fine. If you don't worry. Let's take it just as a convenient parameterization where now all the degrees of freedom are included in this group element. So now what we did is we sort of used all these observations and thought a little bit, well, more than a little bit. And then here's the answer for how to find all the Lagrangian coefficients. So inspired by the generating formalism and the Lie algebraic flavor, the idea is to say, okay, let's put all my coefficients in this generating series in two formal variables with this structure, which is dictated by the model. And let me give you a formula now for this generating Lagrangian multiform and then check that it works. So what's the formula? It's got a kinetic part, which involves the group element here that I introduced before. So this is where the trick of working with Q in this form is important. It's because it allows you to write this kinetic part. So here you have the dynamical degrees of freedom encoding in phi. Here you have all time derivatives encoding in this generating derivative, if you like. And the potential term has this special form, which at the time we found just by brute force calculation, but in hindsight is very natural, as we'll see in a minute. So this is the formula, this is the proposal, and then you just check that it gives you a Lagrangian multiform, and that it gives you the equations you want. So that's the theorem. You take the formula, you look at the variational equations, and they reproduce exactly the equation I wanted to reproduce. So that works. Remember, so this is the equation that contains all the equation of interest in the hierarchy. And to qualify as a multiform, it has to satisfy two things. So it should satisfy the extra conditions, the corner equations, but that works in that case. And the closure relation should hold on these equations. And it does, and I will tell you more about this in a more general setting, because the reason why this works ultimately is related to the classical Yang-Baxter equation. So we'll see that again in a minute, but in a more general case. Okay, and if you want to extract each individual model, well, you have a generating series, so you look at all the possible residues, you recover your Lagrangian for two pair of times. And if you calculate the Euler Lagrange equations for each, you recover a single zero curvature equation. So in particular, if you specialize to the first three times, L12 and L13, you should recover the Lagrangians that we had to start with, that we knew from before. And indeed it works, but now you can also compute all the higher ones systematically if you want, because it's just doing some series expansion. You have everything you need. So now let's move, let me just check, are there questions? So now let's move to the more general context. So in fact, this simple example, well, now it looks simple, but at the time it wasn't so simple, has a lot of key features which can be generalized. And these are the main observations that led to this paper with Benoit and this is my student at the time. So the potential term that I sort of came up with in the example below, the structure of its structure is not random. Actually, it has a very characteristic form, and you can rewrite it with a term involving this R matrix that we've seen before. So this is not random. So it's based on the property of this permutation operator, that the trace of second space of P12 Q2 gives you Q, essentially. So it's a strong indication that the R matrix and the classical Yang-Baxter equation should play a role in this multiform theory, and it does. A second observation, and once you notice that, you say, well, then maybe there's nothing special about this one. What about if we use other classical R matrices? Why not? Then all the series we were working with, all this generating formalism, involved series in 1 over lambda and 1 over mu. But in fact, this is a signal that you're working around a point at infinity. So what about considering other points on the Riemann sphere? And finally, again, in the example of the AKNS, we were working with the Lie algebra XL2, and we fixed this particular choice of the first matrix Q0. But why do that? Maybe we can allow more other finite dimensional Lie algebras and take other choices of starting point of the matrix Q0 to construct different phase spaces and different models. So indeed, what we did is to say, well, yeah, these 3 observations and these 3 questions, you can realize it. You can do all these generalizations and then obtain multiforms for a very, very large class of ultralocal field theories. So I'll try and give you some of the ideas about how we did that. It's a bit technical, so I won't go too much in the details, just give you a roadmap. And then I will show you some examples of how you use the formalism to get other examples, the new examples. Okay, so how do we implement these ideas mathematically? So you have to use an idea, a context called the Lie algebra of G-valued adels. Essentially, it's a generalization of the loop algebra of SL2 that we've used. So it looks a bit scary the first time you see it, but the idea is that you consider now objects that are not just formal series, single formal series valued in SL2. You allow yourself a collection of formal series with a finite number of them being Laurent series and all the other ones being Taylor series. And the coefficients are valued in your favorite Lie algebra, G, instead of just SL2. So a typical element of this Lie algebra of G-value adels is a collection indexed by points in CP1, but only a finite number of them are actual Laurent series. All the rest is Taylor. And this lambda A is a local parameter, formal parameter around the point A that you work with in your theory. And at the point of infinity, the natural local parameter is 1 over lambda. And that's the case, actually, that we were discussing so far. Okay, so that's, if you like, the algebraic arena, the analog of FNR for what we want to do. And it is quite flexible, so it gives you the flexibility to work around other points, so locally, but algebraically. And the other technical result we need is that was in the background of what I explained. So remember, there was this object Q that was just a pure Taylor series in 1 over lambda, and then we had polynomials that were in another half of the Lie algebra. So here we have an analog of this result, a decomposition of this algebra into 2 subalgebras. And this decomposition is controlled by the R matrix. That's quite a generic feature. And we looked at it in detail in our paper for 2 cases. So the original case, rational, but also another one called the trigonometric R matrix, which is a bit more involved. This P12 is the same. These are projectors, if you like, on upper triangular and lower triangular matrices if you work with GLN or SLN, for instance. So this is the analog of this decomposition. Okay, so it's a bit technical, but it gives you everything you need. And now let me show you the schematic implementation of the generalization we can do. So as I said, you trade SL2 for your favorite semi-simple Lie algebra, say. Instead of having just a point of infinity, you take a finite collection of points on the Riemann sphere. Instead of having just a single hierarchy of times that will correspond just to infinity, you're going to have a collection of hierarchies of times labeled by the points in this set. Instead of having a single generating derivative containing all the times, you get a collection of similar objects containing all the partial derivatives. So this is compounding the hierarchy idea, but generalized to this set. Instead of having a single series in 1 over lambda, you have a collection of Laurent series labeled by the local parameters. And similarly, the group element, you've got a corresponding collection of group elements that allow you to do the formal dressing. And quite importantly, the choice of the object you dress with this group element now in general is going to be essentially it's a rational function with poles in the set that you've decided to start with. So that object together with the group object is what controls the phase space and the model that you're going to work with. So we'll see examples later. So once you fix that and once you fix this, you've essentially fixed the model you work with. And the type of model, so if you want it rational or trigonometric, for instance, is controlled by your choice of R matrix. So here I say, I said any skew symmetric. In the paper, we only did in detail rational and trigonometric, but you could imagine elliptic if you're really motivated. It's a bit more technical, but it's feasible in practice, in principle. So you have this machinery. Oh, sorry, and there's one more. Oops. There's one more, of course, generalization. So instead of having a single generating series for all the Lagrangian coefficients, you have a collection of generating Lagrangians centered at each pair of points, A and B, in your theory. And in practice, if you want to look at all the possible Lagrangians that you have, you can extract them by this residue formula. So there's a lot of information there, but the idea is that we have a way to encode all the objects that we want algebraically, and then you can extract all the information you want in your hierarchy, so the Lagrangians, the lax matrices, for all the equations of motions, algorithmically and algebraically. So you compute residues, you do series expansion. Similarly here, you do some series expansions, and you get all your lax matrices. So that's the key message of this quite heavy machinery. Which is what I just did here. So if you're interested in one of the zero curvature equations somewhere in your hierarchy, extract the Lagrangian coefficient from your Lagrangian multiform. You can also compute the corresponding lax matrices from this formula, and you check that your equations of motions that are in zero curvature form are nothing but the Euler-Lagrange equations for this Lagrangian. Okay, so yes, I should go quickly. So the main results before we go to some examples. Well, they're the generalization of the results we had before. So you check that indeed you're producing the equations you want. So the Lagrangian multiform in generating form does produce all the hierarchy of lax equations. So here the notations are a bit more involved because we're working with more complicated Lie algebra, but it's the same content as before. So this is a single generating equation that contains all your zero curvature equations repackaged in a single equation. And these flows commute, so they're compatible because your R matrix satisfies the classical Yang-Baxter equation. Importantly, so now I go back to one of the main messages, the closure relation, which should hold, is a consequence of the classical Yang-Baxter equation. And for this one, I'd like just to show you the sketch of the proof. So it's computational. You could just compute this term here, which is the generating form of the closure element. And after some computation, you convince yourself that it's proportional to this expression. And in the expression, you see the classical Yang-Baxter equation appearing. So if that's 0, then the closure holds. So that gives a variational interpretation of the classical Yang-Baxter equation. Okay, let me skip that. Okay, so how to get examples, because if you're interested in using the theory, not just the theory for itself, you need to know how to do that. So you fix some data, and then the examples come out for you. So fix a skew symmetric R matrix, a solution of the classical Yang-Baxter. So we did rational or trigonometric in the paper. You fix a divisor, so a collection of points together with some integers, and that controls for you a choice of rational function. So you pick your favorite rational function with poles in the set S and with order controlled by these integers, and fix your favorite Lie algebra. So again, for simplicity, let's do GLN or SLN. And once you fix all that, everything is computational, your model is fixed, and all the quantities can be computed. So let me show you, if you want to recover the original AKNS example that I used as a motivation, you fix this data. The point at infinity, this number of the divisor is 0, G is SL2, and this rational function is just a constant here. You choose the rational line matrix, and you can reproduce everything. Now, other examples. So if you want to do the sine-Gordon hierarchy in light code coordinates, so that's this equation here for field U. The data is a bit different. Now you choose 2 points on the sphere, 0 and infinity. They all both have order 1. You still keep SL2. And your choice of rational matrix is a bit different. So sigma plus, sigma minus are the usual matrices constructed from the poly matrices, sigma 1, sigma 2. So with this data and the trigonometric R matrix, you can produce the entire hierarchy of the sine-Gordon equation, and you do the computation. Let me show you examples. So if you're interested in finding all the Lagrangians, well, you can reproduce the known Lagrangian for sine-Gordon in light cone coordinates, but you also discover that the modified KdV is part of the hierarchy, and you can compute an explicit Lagrangian for it. And then you have a mixed Lagrangian that combines x, y, and z, which are the independent coordinates of these two. And it is what it is, but it's part of the hierarchy, and its equations of motion hold consistently with these. And you can keep going. You could go higher and higher in the hierarchy if you like. Another important class of models that is contained is what we call Zakharov-Mikhailov models, because of the original paper where they did just one Lagrangian, but now we generalize to an entire hierarchy. So if you've never heard of these, they're the analog in two-dimensional field theories in terms of being master models of Godin models for finite dimensional systems. So they're very generic. They correspond to Lax matrices that are rational in a spectral parameter with quite arbitrary structure in the Lax matrices. And for this class of models, we can use the rational R matrix, and that would correspond to the original Zakharov-Mikhailov, but you can also adapt them to the trigonometric case, and then we obtain a plethora of new models in that case. So it's a bit general and abstract, but maybe let me show you perhaps the most famous example in that class, which is known as the Falayer-Freshetik version of the principal Carrel model. So you take only two poles, you pick F in this form, and you can compute the first matrices. Take maybe a form that is familiar to you. So it's got some currents, J0, J1, associated to the pole A and minus A. And the equations of motions, they take the usual form for the principal Carrel model. You can compute the Lagrangian for that. And if you so want, you can do all the higher orders. So see what other equations are in this hierarchy of the Falayer-Freshetik model. So yeah, as I said, so you can keep the same data and change R from the rational, which was in this case to trigonometric, and then you get an anisotropic version of the Falayer-Freshetik model. You can specialize that, keeping the data the same, but now specializing B to be the transpose conjugate of A and taking them to be rank 1. And then we got we recovered some models that had been introduced before as so-called deformed Grosvenor models. So it's very versatile. You're only limited by your imagination, really. And everything is integrable by construction and has a Lagrangian multiform description by construction. And sorry, I'm going over time. One last thing, and then I will stop, is it's quite versatile. You can couple hierarchies. So let me show you how to do that on, again, the simplest example. So imagine that now I take two examples that I looked separately, and I want to couple them together. It's very easy to do that in the formalism. You take the data of Falayer-Freshetik and the data of AKNS. So the point now is A, minus A, and infinity. That's put it together. You keep the corresponding orders of the poles. Let's do SL2 for now. And you choose F as a linear combination of the two rational functions that would be determined, that would determine each hierarchy separately. So this contribution is for Falayer-Freshetik. This contribution would be for AKNS. And I couple them with some coupling parameter alpha, which interpolates between the two extreme cases. So alpha 0 gives you Falayer-Freshetik, and taking alpha to infinity in a careful manner recovers the other one. But other than that, it's coupled. And let me show you the type of equations you get. So you see, let's look at the first two because they might be the more familiar ones or easier to interpret. So these two parts are the principal Carrel model equations, and now they're coupled to the nonlinear Schrödinger level of the hierarchy via the coupling constant. And then this is the other way around. So you have equations that would be for nonlinear Schrödinger that are coupled to the currents of the principal Carrel model. And you can compute all the Lax matrices, the Lagrangians, etc., etc. So perhaps I will conclude now. I should conclude. So, well, we've done a lot, but there are many open questions. So it was all about ultralocal field theories, but what about non-ultralocal field theories? I find Godin models, which is something that Benoit is very keen on. Very recently, we actually understood the connection. Let me show you. So we understood the connection between Lagrangian multiforms and holomorphic topological gauge theories in the context of 3dBF and Hitchin integrable systems. So that's just been accepted. But of course, this is kind of the beginning of the story in terms of the relation to holomorphic topological gauge theories. So what about understanding a connection with 4D Chern-Simons or even higher 5D Chern-Simons and things like that. And all this is classical, but obviously also big motivation would be to understand a version of multiform path integral quantization. What does that mean? Can it help us quantize integrable systems? What's the link with the usual quantum Yang-Baxter machinery? I will stop, and I apologize for going a bit over time.
Okay. No, thank you very much for excellent talk with very useful examples. Yeah.